Welcome everyone to the last evening of Avalon Rising. Please come in, take your seats for a remarkable experience which you're about to have with Nick M, who's going to be talking about sacred geometry in a rather spontaneous and fun way. So welcome to Nick M's Sacred Geometry Play Shop.
Hello. Well, thank you very much. To this evening's introduction to sacred geometry. It's described on the normal posters as a journey, a roller coaster ride from the dot to hyperspace with no previous experience necessary. That's exactly what it is. I'd like you to remember as we go through this, I'm going to do a bit of description, but there's always going to be pictures of, or nearly always pictures of what I'm talking about. So you can kind of imagine it in your head, but I'll show you pictures of it anyway. Bear in mind that actually the geometry is going to be doing all the talking to you. You've got resonant counterparts for all this stuff inside your bodies, and all I'm doing here is spoiling the silence. So it doesn't really matter too much. The thing is, it's a really beautiful story. It's got a bit of a density warning on it. There is an awful lot of material in this talk. We're going to do basically a term's work in about an hour and a half. Also, to my knowledge, the information actually in this form isn't available in sort of a printed form or anywhere else. It's been kind of assembled from a whole load of sources, to which I'm really grateful, really. But so you will find yourself wandering off a little bit every 15 minutes or so. It's very difficult to concentrate anyway, but believe me, the information will go in no matter. Each of us are made up of billions of lines and centers of vibrating energy, and the distribution of this energy is governed by the same geometries that define the cosmos. From the tiniest quantum event through all of biology to galaxies and the hearts of stars, these are the shapes that consciousness built, that make the house that consciousness built. There'll be no sums in this talk, just shapes and images. Your biological system is already ready to receive all of these bits, and sometimes there won't be time here. Sometimes I can do kinesiology, which shows that these are physically welded into your system, these shapes. Having said all of that, considering it's so intimate to you, it is, of course, it's pretty unfamiliar. The very phrase itself is a bit puzzling. Sacred geometry. We've heard a lot in this tent this weekend about geometry. Geometry is the measure of the earth, if you like, because Earth is where we discovered it all. Actually, I prefer to define geometry as the way that number fills space. So we're going to see how it moves from a simple dot into all of this multiple forms that we've got in front of us. The word sacred also, of course, is a little bit difficult. You can find lots of dictionary definitions. I choose to define it as that which remains whole over time, because we're aware, are we not, that our science is constantly being rewritten. As something's discovered, the thing that we thought yesterday is no longer believable. Same with our religious texts. They get developed over time. The Bible gets kind of tweaked about every 200 or 300 years to make it suitable for the population to which it's currently being presented. Well, the information we're looking at tonight is older than all of our oldest texts. It was probably written down about 350 BC by a chap called Euclid, who was a Greek. And since that time, it hasn't changed. This information has remained absolutely consistent, and that, in my opinion, is what makes it sacred. We've learnt a little bit more about the nature of geometry. We've learnt a whole lot more about how it applies. I mean, anybody who saw John Byde's talk, or the talk earlier on this afternoon with the house-whispering gentleman, Christian, all of those were applications of the basic principles I'm going to talk about here. It's at the foundation of the human design. Your immune system is geometrically based. That's how, in its uninterrupted, in its uninterfered with state, your immune system can deal with things that have never been seen on planet Earth before. And that's because these geometries are true throughout the cosmos. Whatever it is you get in your system will be geometrically based, and so can be dealt with a geometric solution. Your immune system knows this, right at the heart of you. Much of this also can be done with no maths and no protractor, no means of, if you like, of measuring angles. You can do it on a piece of paper just with a straight edge and with a pair of compasses and a pencil. If you're doing it outside, you can do it with a peg and a rope on the ground and some spray paint or sand or what have you. It's very simple. I always recommend that if you feel fired up by what you see here, then one of the best ways you can engage with this material is to go home, get a piece of paper and start drawing it. And eventually you'll find yourself doing these marvellous things that Louise has done for us around the place. This is where geometry leads you if you start experimenting with it. The principles of this geometry have been used in all of our sacred spaces as well, so it doesn't really matter whether you're dealing with a burial mound or a barrow or a church. All of them will be bounded by these geometric boundaries that we're talking about. So that's a quick intro. I'm going to start off with a nice simple shape for you. Hopefully, can everybody see that and still hear me all right? This is, everybody okay with that? Do shout, because I can't see you. Yeah. Yeah, this is going up and down a little bit. Try standing back. Oh no, quite sure. I'll leave that. Leave that. Try that again. Try that again. Testing, testing. Thank you. So we're going to start off. What I'm doing is I'm starting off. I need to talk to you a little bit about some of the basic principles we're going to be investigating. And one of the things we're going to be looking at again and again and again is the business of self-reflection. I'm choosing to start with triangles because it's a nice, easy shape for us to deal with. This big pink triangle in the middle will actually hold 4 of the green triangles. So you could put one green triangle in there, one in there, and one in there, and that would leave room for one green triangle in the middle. You could fit 4 orange triangles into the green triangles, 4 yellow into the orange, and 4 pink into the yellow. So what's happening here is each triangle is effectively a quarter the size of the one above it. And you can already see, can you not, that we're getting a lot of beauty from just replicating a half-size triangle and sticking it onto the edge. But there are other quite remarkable things about this shape. For example, although I started with the pink triangle and stuck all the others on, if you look down here, you can see that they're all forming a straight line. Can everybody see that? These triangles here, despite the fact they were added, if I drew a triangle round this triangular shape, I could keep adding and add an infinitely sharp pair of scissors and an infinite supply of coloured card. I could keep cutting smaller and smaller triangles and sticking them onto this, and they would never break outside the line. That's one of the important things about living in the 3rd dimension, is that you can't grow without taking up the space of something else. If you put something in a box and grow it, eventually the box will become full. Well, one of the things this is telling us is that in a certain way, things can grow. The surface area of this can grow infinitely as I add more triangles to it, but it would never step outside its original bounds. Now, that's something that happens in higher dimensional space. Somewhere in higher dimensional space, all of us are sharing a space energetically, and you wouldn't be able to see the difference between us. The 3rd dimension is here to separate us. And that generates directly this sort of beauty. Now, of course, I can use the same triangles to grow the thing inwards as well. So there's a green triangle with an orange triangle, with a yellow triangle, with a pink triangle. So once again, you could keep adding more and more triangles to this, and it could grow inwards and outwards without ever treading on its own feet. Another important thing to notice about this is the idea of an upward pointing large triangle with a downward pointing small triangle inside of it, because that we are again going to come across time and again in this talk. So I'll just rest that down there. So that's a fairly simple version. This is another self-similarity. This one's been generated on a computer, so some of the shapes have been slightly squashed a little bit. We'll look at a purer version in a minute. This is a slice through a 7th dimensional hypercube. Now, I only know that because the guy that did it told me. That's Mick the Moon, the man that makes the moon calendars, does these for me. The thing is, it's basically made out of about 3 different shapes, really, and we'll look at, like I say, a purer version. You've got these, and these. 3 different shapes of diamond. Now, one of the things about this, you're all going to be having a lot of difficulty keeping that flat on the screen, are you not? Can you see spheres and cubes kind of wriggling in front of you? Your eyes just try and, it's a 2-dimensional thing. It's a flat, plain thing, but your eyes, because you are who you are trying deliberately, just constantly trying to pull it out for you. Here's this is an uncomputer modified version of the same thing. Now, see the center of the design here? Again, this is looking really 3D to you all, I hope. It's really wriggling around, but if I ask you to, and it looks really, what's the word? uneven, looks kind of unbalanced. Your eye's constantly wandering across it, trying to find a pattern. Well, if you look at this 7-pointed star in the middle here, and then let your eyes just move in rings out to here, and then out to here, and then further and further out, and what you should see is something that's actually very, very balanced. It doesn't look like it to you, but that's because it's got 7 points in the middle and not 8. So your eyes are trying to sort that out. This is called a Penrose tiling, and once again, this shape is made out entirely of that shape, and that shape. There are only 3 shapes making all of that. I have it in mind one of these days to make some cement moulds so that I can have a patio that looks like that. It's really far out. So that's one. These are kind of forms of fractal, really. We call this growth by self-similarity fractal growth, where things can just develop with the knowledge they've got, and where each little bit contains enough information to rebuild the whole system. Modern versions of these, is that right? Are we going to do that? Okay. Right. Oh, well, that is a major nightmare. I'm not using my own computer, and these slides are no longer in the right order. So I'm just thinking about how exactly I'm going to deal with that. With some bloody difficulty, I think. Very difficult to do that, John, because none of these aren't where I want to go at all at the moment. Also, they're all squashed, so they ain't going to look very good. Right. In that case, I'm just going to have to try and talk you through it. Oh, no, that is... Right, okay. That's what we're going to have to do then. They're numbered, they've got numbers at the beginning of the file name, so they should turn up in order. That's why I do it, but it's a Mac, it likes to take control. I'm just going to have to wing it then, guys, I'm sorry. No. So what would normally happen at this point? What would normally happen at this point is I would show you a fantastic multicoloured picture of a Juliet or a Mandelbrot set. It's absolutely amazing fractal. The actual maths for doing fractal designs like that were first thought up by a chap called Leibniz about 200 or 300 years ago, but we couldn't actually produce fractals so that we could look at them until quite recently. And that meant that we could see these fantastic coloured shapes that were forming as a result of very simple arithmetic expressions. Subsequent to that was going to be a picture of a cauliflower, which is actually made like a Mandelbrot set. So we've gone from having the maths and not being able to see it, to being able to generate it and put it on a 2D screen as a plane, to being able to generate it as a cauliflower. So I really like the way these discoveries are leading us towards ever more and more kind of complex understandings and visual understandings of what it is we're dealing with. I want to talk a little bit about dimensions. It's quite hard for us, being 3-dimensional creatures, to imagine what it might be like living in a 2-dimensional world. And we're going to be dealing with plane shapes. This is a triangle. It's a plane because it's kind of flat and it's got no edge to it. One way to imagine life in a 2D world would be to, say, take the surface of a lake. You're standing at the edge of a lake, and just imagine that on the top of the lake there's some creatures, and they've kind of got width and length, but they haven't got any depth at all, no depth at all, so they just exist on the surface of the water. Now, if you imagine you go and put your leg into the water, these creatures are just going to be aware that a hole's forming in the middle of their community. The guys around the edge won't see anything, but the critters around your leg would just be aware that they're moving apart. Because they're 2D, they'd have absolutely no idea that you've got this body up and the sky and the sun and all of that, and they'd have no idea of your legs reaching down into the mud either. They would, just like I say, see this kind of hole. Now, some of you might have seen, I think it's What the Bleep, they actually had a kind of a demo of how that would work. The slides I normally use show what would happen as a sphere drops through flatland. So if you imagine you've got these creatures that have got width and length but no depth, as a sphere comes down into their world, the first thing that will happen to them is a tiny little hole will appear in them. And then as the sphere falls down, the hole will get bigger. Once the sphere is halfway through flatland, they'll have a big hole in the middle, okay? Now, the guys at the edge, they're just going to be aware that they're getting a bit crowded. Nobody can look above it and see anything. We'd be able to if I had the slide, because we're three-dimensional critters. As the sphere disappears, as it starts falling below flatland, the hole gets smaller, and once it's almost disappeared from flatland, they just have a little dot, then pluck. Now, they've got no idea that was a ball. All they've seen is a series of different circles with no thickness on them. If you dropped like a pipe, something like a smoker's pipe with a pipe stem on it, as that goes into flatland, as the bowl goes into flatland, you just get a little dot. And then as the bowl falls further in, you get a bigger circle. And then maybe this bit of the pipe goes in and that bit. So you'd end up with some little shapes as well as the circle. And they'd change, they'd elongate, the circle would get smaller. And once the pipe's disappeared, again, it's no longer there. Now, the thing is, because of the way the pipe's built, what the creatures would see is just a series of apparently related but not connected events. Now, we can see the second dimension because we're above it. I can see this plane thing because I can look down on it. I'm a third-dimensional beastie. Now, one of the theories is that we can only see a dimension because we live in the dimension above it. So we might say that because we can see the third dimensional, we must be at least fourth or fifth dimensional entities, which is an idea to which I particularly adhere. You can do stick diagrams. We've seen, you can see how this thing wriggles about. You can do a diagram of a cube that does the same thing. When you look at it, if you look at it one way, the front of the cube will be pointing at you. And if you look at it another way, the back of the cube will be coming out to you. And you can only see one of those things at a time. Just as this is twisting around, you'll only be able to see it in one state. So, but you will not, you'll find it very, very difficult to make it two-dimensional. So, I actually then have some amazing pictures using chalk on streets. People have made like a London street look like there's chasms of fire in it, and there's kind of cars parked in amongst all of this, but they've painted it onto the road with chalk. And I've got another one of a guy falling down an icy hole, and it's all just done with chalk, and it's because people are deliberately then playing with your tendency to see 3D. If you look at them on the internet, put chalk perspective drawings or something, and you'll find loads and loads of them. They're absolutely brilliant. They really take your breath away. So, another way we've got of doing that nowadays, and this is the same stuff, same mathematics as we used by Leibniz and Gabor and the rest to come up with fractals. Here I've got, and if I move it around, can anybody see anything happening in there? You can come and have a go at it later, but what it is a hologram. You'll all have seen little holograms that on your check or credit cards or whatever, just a tiny little shiny thing with a bird whose wings move maybe. Well, this is a much bigger one. I invite you to come and play with all this stuff afterwards for a bit. If you get this so that the light's shining behind you over your shoulder and you look at it, what you've got is in the middle, you've got a picture of an owl's head. And if you twist it slightly, either side of the picture, you've got an eagle and some kind of fish-eating bird. Now, they're there in their entirety. They're really three-dimensional. If you get them out into bright sunshine, the picture is almost in front of the glass. Like it's very, very 3D, and it appears three-dimensional. See lots of colour in it. Its eyes look kind of real and everything. And the other two pictures, the other two birds, are just as full. So they're all in this single flat shape. If you look at the hologram in certain kinds of light, all you see is wavy lines, which is actually the hologram's natural state. You're somehow pulling this stuff out of it. Now, we're interested in the hologram partly because it's doing 3D on a 2D surface, but partly because if I was to break the hologram and pick up a small bit of it, then it would have the entire picture in it. Just a little bit of the hologram would still have all three of the birds in it. They'd be lacking a little bit of colour and they'd be lacking a little bit of depth, but they would nonetheless all still be there. And the point there is that in a hologram, for technical reasons that we do not have time to go into, and also I don't thoroughly understand them, it contains enough information to rebuild the whole hologram. Now this brings us on to one of the things that geometry is really good for, is it enables us to understand quite complicated ideas, because just like the hologram, every single one of you, have got enough data in your system to rebuild the entire cosmos. Basically, we're all fractal elements built from the bottom up. So these are all things that are used in generating our real world. Now, That's a trick piece of technology, okay? That's your hologram, pretty expensive, pretty flash, need all sorts of cameras and stuff to do it. Has anybody seen these 3D picture books you can get? These are eye tricks. Some of you will have, they've got several of them here. That look blurry like this one are actually quite difficult to do because you don't know what's going to jump out at you. The ones that have got repeated pictures on them like this one are much easier to do because this just turns up as a 3D picture, but it looks just like that. Now, the funny thing there is you are looking at something which has just got a bunch of swirls on it, just like that hologram. That's the natural state of the hologram. But without any lenses, without any trick photography, without any lasers, your head is pulling 3D out of this flat sheet. Okay? So that's got to make you start wondering about the nature of the dimension that you're living in. The first one of these that I ever saw was a postcard. It's actually on here somewhere. And when it worked for me, I'd tried it for ages and ages. It really took me some time. But what eventually happened was these coloured columns of light just come off the postcard that I was looking at. Swirly patterns they were, and they were so real that you could almost tilt the card and look underneath some of the shelves of colour that were coming out of this thing. Absolutely astonishing. And the other thing is that if you look at the postcard or the book, if you look at the base of the picture as you pull it into 3D, it goes spherical. There's a reason for that, I'm sure. It's because I think nearly everything we do turns out to be spheres. But that's showing you that this idea of dimensions, the first, the second, the third, the naught, they can't actually be separated from each other. They're all part of this dimension that we're living in. So when I pretend in the talk that I can separate them, it's really just for illustration. Geometry itself actually starts with a sphere. We've got one here. The reason why I like to start with a sphere is because everything out there is spheres. If we look out into space, everything that's above a given size will, through gravity and erosion or what have you, will become a sphere. It doesn't happen to smaller things. We live on a sphere. We look out at the world through spheres, of course. And of course, the first cell, all of our cells are spherical. The first cell is spherical. So we're born of spheres. Also, all of the shapes we're going to be looking at today are ways of breaking a sphere into equal parts. And of course, that's what happens to us. First, we start off as one cell, then it divides into 2, then 4, then 8, and what have you. So, sphere is really where it all begins. Now, Leibniz, the man who came up with the maths for the hologram, he called the original sphere, if you like, the giant sphere that existed before anything else, he called it the monad. In our culture, we might call it the face of the deep before spirit moved, the primordial ooze. Whatever it is, it's the thing that existed before other stuff started happening. And at that point, this massive sphere, this massive monad, would have looked, everywhere in it would have been the same as everywhere else. And everywhere you looked would have looked the same. And that, of course, is kind of what we've got now. We've got a kind of Big Bang theory that does the same thing, which we'll reach at in a moment. The Greeks called this to be stable. The monad, it was to be stable and oneness. So before anything there was just that one thing. In the beginning was the word, if we like, and the word was monad. The monad is all there was and is. It's the container of all. It's a sphere whose center is everywhere and whose boundary is nowhere. Geometry starts when we imagine the sphere shrinking itself to just a single dot. So we imagine that massive sphere that was everything just going down to a single dot. Now, that, of course, is a bit like our Big Bang theory. They think the whole place, the orthodox theory has it, that the whole place started as a tiny little dot, which was infinitely heavy and infinitely small, so it had absolutely everything it needed in it, including a few imperfections, which turn out to be the matter that we see around us. Now, that tiny little dot at the point of the Big Bang goes whack, and it becomes absolutely everything. From being negligible, so small you can't see it and containing everything, it goes to be absolutely massive and containing everything. And the scientists tell us that at the moment, the cosmos, it's pretty much the same wherever you are in it, and wherever you look, it looks pretty much the same. So if we were looking out with a telescope, what we'd see is all the galaxies running away from us at an increasing speed, but at the same speed as each other. And in that sense, it's just like our man's monad, really. This is going to be, how are we going to do this? How are we going to be able to do this? I think we probably are. Right. So we've got the dot sitting there all on its own on an imaginary piece of paper. And it's north dimensional, we're saying. And we imagine that it's spirit sitting there in the middle of its monad, just this little point of concentration, thinking, what am I going to do? So spirit draws a circle around itself so that it remembers where it is, and then it moves. Spirit moves to the outside of its circle, and it draws another circle. And it makes the shape that's known as the vesica piscis, which is this shape here. We've seen it many, many times this weekend already in this tent in loads of applications. And I want you to imagine that the line is running across there, just across there. Now, what's happened when spirit does that? I call it spirit, we could call it God, could call it what you like. I'm not trying to be culturally insensitive. But nothing exists without its center around which it revolves, which is where the circles came from. And the Greeks referred to this moment when spirit moves as the dyad, two-ness. It's not different from oneness, it's just one thing pretending to be two and taking itself seriously. And that's what continues to happen. It continues to reflect upon itself as it grows. And the Greeks called this moment audacity because of its brilliance and its bravery in wanting to get away from unity or in moving away from unity. But they also called it anguish because of its yearning to return to wholeness. So do you see the duality? Some kind of cosmic fall has happened there. We've got, instead of just having a oneness, which is all here, we've now got a nominal here and there. Separation has happened. There's a before and an after. There's a light and a dark. And that's just the first dimension. That's the line. And here we've got to imagine the first dimension. This line is it's got length, it starts here and it goes there, but it's got absolutely no thickness at all. So you can see why we have a little bit of trouble with the first dimension. The other thing that's important about this is that this shape in the middle, the vesica here, is called the cosmic vulva, because it's not only the point where all geometry comes from, but it's actually, if you look at it, it's the shape of our eyes, it's the shape of all of the holes in our body of this shape. I don't know why they called it the vesica piscis, which means bladder of the fish, but it is definitely a formative shape, physically in this world, in the form of our eyes, and especially in geometry. It's really hard without my pictures coming up, guys. So this apparently simple image effectively relates geometry to a spiritual journey and the passage of birth. It's this movement into... There's a movement from unity to the material matrix and an arising of opposites. What I normally show at this point is a picture of a thing called an hourglass nebula, which is exactly a vesica piscis. It's two circles of red dust out in space about 8,000 miles away, 8,000 light years away from here. And in the middle, where this is a massive green and yellow eye. So it's like there's been two explosions in space, although the scientists say it is framed by an unknown process, this hourglass nebula, and then the interference of those two forces, the interference of those two rings, creates something in the middle. And we're going to see that that's really how Earth works as well, all this kind of interpenetration of different forces. But so that would be an hourglass nebula showing you basically a giant vesica piscis in the sky. So we've got a line, we've got a nominal line across, I might go and have a go at my pictures in a minute, but so we've got a line across here, which is the first line. It's the first dimension, its length. And the quickest way that spirit can get back to where it started from is to shoot up to this point here and then back down again, and it makes a triangle. And in a way, we could actually stop the talk there, because it turns out that absolutely everything is made up of triangles. And also the important thing about the triangle is it's three in one, triunity. It runs through all of our sacred texts. And that's because once you've got the line, you've got, say, an I and a U, you've got a kind of point at the top. How you choose to resolve that point might well decide whether something perpetuates itself or whether you can bring it to an end and start something new. So the triangle gives us the ability to have a resolution of the opposition from the line. Do you see? So we've already got a kind of balance. And the triangle comes up just in the vesica piscis. Now, because I've seen the next picture, I happen to know it's the one I want now, I hope. These have obviously been completely trashed by the screen. They have been elongated, so they will unfortunately not be singing to you as they should. Oh God, they look fine there. That's interesting. Very good. They look great. Thank you. So what I've got, what would have been here with the original vesica is we'd have had a triangle in there. Okay, ignore the square. Here's the first two circles we did. Now, if we want to get any more shapes out of this, the triangle is the only one that will come out of the vesica. Now, there'll be other people who've got other ways of doing this, but you can see we've drawn a third circle here. Basically, this circle is centered there. These two are centered on each other's sides. So this circle is centered there. We draw a circle, and straight away you can see, if I can pick it out for you, that we have a triple. We've got that Celtic triple knot in here. Can you see that? It's again, this was described earlier as one of the most powerful shapes in creation, though we can't remember the name of it. I'm not particularly interested in the hexagon at the moment. What I'm trying to do is show you how these shapes arise really easily. All of these are done without a protractor. I've drawn all of these just using a straight edge and a pencil. But the reason why the hexagon's there is because it's where we get the cube, where we get the square from. So we've had a triangle, and down here we've managed, can you see how we've drawn a square within this hexagon? As it happens, the three-dimensional version of a square is called a cube, and its proper name is a hexahedron. So it actually is a six-sided, this is connected with that. But, so we can get a square by drawing, we've had a triangle in there, and we've got a square. Those are the first two of the plane shapes that I'm interested in here. If I'm really lucky. There we go, yeah. The third of the plane shapes we're interested in is called a pentagon. And it's got 5 sides, and it looks like that. And in order to do that, in order to draw a pentagon, I've got to have another circle down here. So what I've now got is I've got the circle I originally started with and 3 circles round it. And from those 3 circles, I've been able to pull a hexagon, a square, pentagon, and a triangle. And those are the 3 basic shapes of creation, and they can all be done using this flower life design. We'll see that as we get onto third-dimensional shapes, hopefully we're going to need the other 3 circles down the side. But those 3 plane shapes bring us on to the third dimension. These are all effectively flat, they're lying on the screen. But Spirit decided, first of all, I think, to build with triangles. And here I've got something which I'm going to have to... Here I've got the first of our 3-dimensional shapes. It's called a tetrahedron, and you'll see as I move it around, it's all made of triangles, and no matter what I do with it, it looks the same to you. Now, it's got 4 triangles on it, which means effectively this could have started with a triangle, thrown it up here, and it's got 3 more triangles. It's got 4 sides, 4 faces on it. All of the sides are the same length, all of the faces are the same size. And if I was to put a sphere around it, the points would touch the sphere, but the faces wouldn't. If I was to put a sphere inside it, the edges of the sphere would touch the faces of this, but not actually the edges. And that's, if you like, the true nature of opposition. It's more a matter of cooperation. Plato, after whom these 5 shapes at the front are called the Platonic forms, and they're the simplest way of dividing a sphere. This divides a sphere into 4 triangles. This one is an octahedron. It's also made out of triangles, and you can see that the same thing applies to it. No matter how I move it around, it actually looks the same. It's got 8 triangles, all the edges are the same length, all the faces are the same size, and again, if I were to put a sphere around it, the points would touch the sphere, but not the edges, and if there was a sphere inside it, the sphere would kiss the faces of the form, but not touch the edges. Plato associated this with air, and prana. Well, we associate it nowadays with prana as well. I'm not sure Plato had a word for prana, probably did. He associated this one with fire. The third shape of these 5 that's made out of triangles is the icosahedron. It's made out of 20 triangles, or again, once all the triangles are the same size, and no matter which way you look at it, it is the same. So this one divides a sphere. If you put a sphere around it, basically the points would touch it, but not the edges. If you imagine that these were inflatable, imagine if I was to just blow in here, you can see how this would become a ball. So this is a way of dividing a sphere into 20 triangles. Now, the other 2 shapes are the cube and the dodecahedron. I like to think that as Spirit created the octahedron, which is a pretty unique shape. The pyramid at Giza is probably the only pyramid in Egypt that is genuinely this shape. All have got less steep slopes on them. That's why the pyramid at Giza is a precise geodetic model of the Earth, if you like, is because this fits exactly into a sphere, whereas the other triangles, the other pyramids don't. They put a special lot of effort into it. Very, very difficult to build this in stone. But I like to think that as Spirit built these with triangles, it saw the square. Can everybody see that there's a square in here as well as a triangle? Because there's 4 triangles, really. They've got to have a square at their base, haven't they? Well, I like to think that Spirit thought, I wonder what happens if I fill space with those. And it came up with the cube, the most familiar of our Platonic forms. And that's connected by Plato with Earth. Similarly, I like to imagine that as Spirit built the icosahedron, which is the symbol for water, and interestingly, the molecular structure of water is very much like this. It's got 5 points, and that's what makes it so versatile. But it's also, as you can see, because it's got 5 triangles, at the base of those 5 triangles must be a 5-sided form. So Spirit might have seen that and thought, what happens if I fill space with that? And you end up with one of these. This has got 12 faces on it. It follows the same rules as all the others. All the faces are the same, and a sphere would fit around it, and the points would touch it, and the edges wouldn't, and all of that. 12 5-sided faces, and Plato associated this form here with ether. Those forms are the only 5 ways of dividing a sphere into equal portions, apart from the Chestahedron, or whatever it's called, John, which isn't included in this talk, alas. This one divides a sphere into 8 triangles, this one into 6 squares, this one into 4 triangles, this one into 20 triangles, and this one into 12 pentagons. Now, the thing is, it's now been arithmetically proven that there isn't any other way, really, of doing that. But all our other shapes develop from that. All the other shapes we're going to look at grow from these 5. And in a way, they all grow from the triangle. But before we see how these other shapes grow, I'd just like to have a look at another aspect of this. This is going to involve a little bit of work. I'm going to see what picture comes up next when I press the button. We'll just have to... What I'd like you to do is imagine that instead of this, you can see that it's like a dice, and we normally have 1, 2, 3, 4 on each face. I just want you to imagine that there's a single dot on each face of this cube, okay? And then I want you to imagine that this spot on the top is connected by little beams of light with the dot on here, the dot on here, the dot on here, and the dot on there. Okay, everybody happy with that? If you're not, say no. Excellent. Dot on the bottom is also connected by little beams of light to these faces. Okay, is everybody happy with that? You should be able to have a shape in your mind now. I'm not surprised. Hopefully the picture I want will come up next. No. No. Sorry guys. Now I know what's coming up though. That's useful. All right. Okay. How about this? Right. How about this? I'm going to need... There we go. I'll just squash my octahedron. Okay, because we haven't got the pictures, that's what you've got basically. Because this has got a point at the top and a point at the bottom and 4 points around the edge. And this has got a spot on the top, spot on the top, spot on the bottom, and 4 spots around the edge. It's this, okay? Happy? Yeah, you can see if I hold it up, you can see how, if this was smaller, it'd actually fit in there. Well, obviously the same thing applies to this. If I put a dot in the center of each of those 4 faces and join them together, I get a square, do I not? And because this is the same no matter which way you look at it, there must be another square here, another square here, another square here, and another square at the bottom, giving us a cube. So these 2 things, earth and air, which look like separate things, are in fact reflections of each other. They're kind of etheric opposites. And that, once again, is an indication of how opposites are. They're supposed to lead to progress and to building things up, not to a kind of contraction and collapse. Opposition is really a form of balance, and the geometry here is showing us that. Now, if you imagine that in this cube you've got a very, very baby one of these, okay? Imagine that this is smaller and that it's living inside here. And imagine that this starts growing. What's going to happen is the points of this octahedron are going to come out of these various faces, and then I want you to imagine that the octahedron grows until its edges are the same size as this. And what you'll get is something that I'd really like to show you a picture of, but I can't, so I'll have to show you the real thing. It is, in fact. See this here, this one? Can you see that there's a cube here? You've got the square face of a cube pointing at you, okay? Is everybody happy that there's a cube in the center of this design? It is. Yeah. And could you also see that there's an octahedron in it as well up here? So what we've effectively got is a cube nested inside your octahedron. So it makes a new and rather beautiful shape. Sorry, speakers. Right. Now, that's another thing, is these things really, they're like photographs. It's like a photograph of a waveform. That's much more what the geometry is actually like. It's like a pulsating imaginary thing, but they do spin very well, you're right. Well, if we now move on to our dodecahedron, if we imagine that there's a point, a dot in the center of all of those faces, and you join them together, because there's 5 faces attached to these 5 edges, what you're going to get, and you'll have to take it. I've got pictures of these as well, but they're going to come up at a random rate. You get one of these nested inside one of those. This is a major nightmare. So, and the same thing applies to this. If we put a dot in the center of each of these faces, because there's 5 triangles on each of these, what you end up is one of those in the middle of it. So these two also, this is water and ether. These are also reflections of each other, the 2 universal growth media. So rather than being separate things, they also are kind of etheric opposites. Now, if again you imagine that we've got a baby one of these living inside here, and this starts growing until the edges of this and the edges of that are the same length, you also end up, you will not be surprised to hear, with another shape, and it's this one. So here we've got, now if I point that towards you, can everybody see that there's 5 triangles which I shall outline now? One here, one here, one here, one here, and one there. So they're all pointing towards you, the triangles, okay? So hopefully you can see from that there is one of these, and then you can also see that we've got a 5-sided shape here. It is very difficult to see. Here we go. It's there. Yes, it's actually a lot easier when that's why I have pictures on here as well, so that you can see the solid thing. But I mean, what I could do. Oh, here we go. Oh, fuck. It's very difficult. It's very difficult for me, this, really. Well. Right, okay, then I can pick the ones I want. Oh, well, that's...
And there'll be more there as well if you go through. Or you can use your mouse.
Right, no. Right, we'll just leave it like... Thank you very much, that's great. How do I get out of these once I've picked one up? So if I do that one... Okay.
Happy, Teddy?
That one, and then how do we get out of it again?
When you move it, see the multi.
Yeah. Oh, okay. Right. Oh, brilliant.
Proper Mac person.
Okay. Right. No, that's great, Tart. So here we go. Look. Here's one. There we go. Thank you very much, sir. Much appreciated. Okay. So now we can see it, can we not? This is the second one, the one we're just looking at. You can see there's a dodecahedron in the middle. You can see that its corners are in bang in the center of the faces of the triangles. It's a very difficult thing to draw. And oh, there we go. There's the other one. There's the icosahedron inside the dodecahedron, okay? And the shape we're looking at here is that one, okay? So hopefully that makes it a lot easier for you to see. That's why I try and do them on the screen and with these, because they look thoroughly different. This one has got, you can see, here's the icosahedron, there's your 5 triangles, and you can see the dodecahedron is here, okay? Now, an interesting thing about these two shapes is that if I hold this one up, you can see that there's a big triangle with a little upside down triangle inside it. Can everybody see that? Yeah, okay. Same thing's true of this one. I'll just point it out. Here's a downward pointing triangle and an upward pointing triangle. Same thing, okay? So not only are these two shapes made up of two forms that we've already identified, they're both actually made up of, somehow, they're both made up of planes which contain a big triangle with a little triangle inside it. That leaves us with one of our original shapes, this one here, which is the tetrahedron. How many things can you juggle at once? I don't normally use a mouse either, you see, so... Hey, here we go. It's not on the page, that one. Right, okay, we'll have to... Oh, there it is. Okay. If you put a dot in the center of each of the faces of this and a dot on the bottom, and then join the 3 dots on these faces with the dot at the bottom with beams of light inside it, what you'll see is a baby one of these, but upside down, like this. There we go. So what we've done there is we have a tetrahedron with a baby tetrahedron inside it. And if we imagine that this small tet, the contents, grows so that its points come out through the center of these faces, and it grows until it's the same size as its container, we end up with a star tetrahedron. And that is this shape here. Now, this is the one that really turned me on to geometry. I was not interested in geometry at all until somebody showed me one of these. Actually, it was one like that. It's really, really useful, this. I could do probably a whole talk on the star tetrahedron. So it's better to go without questions until the end, because otherwise we can really get diverted at this stage, because everybody has different ideas as to what this is, and all of them are right. What we've got is a tetrahedron pointing upwards and a tetrahedron pointing downwards. I've tried to make it so that I could have a blue upward pointing tet and a red downward, but I haven't done that. I couldn't do it, so I put shiny critters on the upward pointing one and not on the downward pointing one. Can everybody see that? Okay. It's a very, very fascinating symbol, because we can imagine that instead of growing one tetrahedron inside another, you can imagine one of them pointing up from the ground and another one pointing down from the sky. And as they come down, they kind of interpenetrate each other and make this sort of shape. And that's what happens on the Earth every morning. Every morning, all of the feminine energies of the Earth reach up to the sky. You can see the birds waking up, the flowers, some of them really do look at the sun. And at the same time, we have the sun itself. We have information, light, energy, all the stuff we need. And it's the interpenetration of the matter of Earth and the light coming from space that actually makes all of the Earth and stuff possible. So when we look at this star tet over here, we see that if you look at this, this also is made up of a big triangle with a little triangle upside down in it. So all of these pairs are really made up of the same thing. What I'd like to do is just quickly, I want to show you just quickly. Go for that one. I just want to show you quickly how these three, because I would have normally run through these as I introduced the three-dimensional shapes, so that you could see how when you've got the whole flower life, when you've now got a circle in the middle and 6 circles round it, and that enables you to generate things that look like the three-dimensional shapes. So we use the 3 circles on the left to build two-dimensional planes. When we add the other 3 circles, we can start building 3-dimensional shapes on a 2-dimensional surface. All of them will do that. You can grow, you can get. There's the cube in the center of the flower of life. There's the octahedron and the tetrahedron in the center of the flower of life. And here's the octahedron in the center. Oh, that's not, we've done that one, sorry. It's really, there we go. The icosahedron. So all of those can be formed inside those 3 circles. And as you do, those of you who are familiar with the flower of life will know that if you continue that process, you end up with something that looks like this. I should think most of you are now familiar with this design, are you not? Yeah, it was very, very rare up until a few years ago, and then suddenly it turned up, somebody showed it to somebody else, and suddenly it was everywhere. Actually, it is the key to nearly all Islamic architecture. It is, you very rarely see it because it's the thing that lies under it all. It also, in a way, it lies under our Celtic artwork as well, but we build ours on a square base rather than this. Now the thing is that what we've done is we've formed these shapes here, or at least the square, the octahedron, the tetrahedron and the icosahedron, we've formed from the circles that are just in the middle of this thing. If you want to do a dodecahedron, if you want to do the sign for ether, this one, you have to have a much, much bigger version of the flower of life, which looks like this. Here we go. There we go. If I actually want to pull a dodecahedron out of the flower of life, I've got to have the whole thing. Can you see how it's being, this thing is being projected from out here? The lines to draw that are from out here. And actually, we've had to cheat a little bit to do that. Because these are naughty lines. These are lines that are not in the design. I have just discovered, though, that if you add another 2 sets of circles to the outside of it, then you get a proper dodecahedron in there. Also, I'd just like to mention this 5-sided shape used to be one of the big secrets of the world. It did. It was how you got into the geometry club. If you could draw one of those without using an angle measuring device, Plato would go, all right, you're in, mate. So it wasn't until Leonardo da Vinci started publishing his books that anybody actually wrote down how to draw a 5-sided figure. The easiest way of drawing a 5-sided figure is using the vesica, as I've shown you, but there's 2 other geometric ways of doing it that are much more complicated. I want to show you the background on this. You can see there's a sort of star around all of that. That is a thing called Metatron's cube, which looks like this. Right. Okay, now can you see there's a cube in here? Here's one face of the cube. Here's another face of the cube, and there's the third face over there, okay? And imagine all of those red lines are inside there. That basically is a way of showing all 3-dimensional shapes springing from the flower of life. And if I'd been able to manage my technology a little bit better, you would have seen it progressing, perhaps a little more happily. And now we get to the idea of, I just want to whip through the other shapes that go with these. Like that. Don't know where my tetrahedron is. There it is. Oh, for fuck's sake. I'm having a hard time here. Right. Brilliant. That's all right. Is everybody all right? Yes. Excellent. Thank you very much. It all seems, it's all not quite usual to me. There are 13 more shapes in this little box here, which we're going to look at. And the other one is not there. There it is. You've got to laugh, haven't you? There we go. Right. Now, there we go. So, I've coloured these all in so we can see where they come from. Now, these all work on the same principle. This is a genuine piece of new information that surprises geometers, it surprises physicists, it surprises everybody. It's a hard one to explain because not only do I not have a picture of it, but I broke the model that demonstrates it. So, you are genuinely going to have to do the work on this. this is a masculine form, and this is known traditionally as a feminine form. And this is where we start dividing spheres into two different shapes instead of one. So this one's made up of hexagons and triangles. It's called, by physicists and geometers, it's called a truncated tetrahedron. And you can see why it's called a truncated tetrahedron, because somebody's chopped all the corners off it. Now that's an idea that we come across a lot, that by you get a girl by chopping bits off, get a boy by chopping bits off a girl, or whichever way around it went. Well, we discovered that, in fact, if you imagine, what I want you to do is I want you to imagine these three ribs here just floating apart until they're as far apart as they are long. And what you should have in your mind's eye is three ribs that you could join together with a triangle, yes? Obviously, if you've got three of them, when you join them up, they're going to be a triangle. So we can actually grow this feminine form out of the masculine one. We don't have to chop bits off it to do that. That's exactly the same for the others. This tetrahedron, the truncated tetrahedron, whatever we want to call it, takes a sphere and it divides it into hexagons and triangles, six-sided and three-sided forms. The same rules apply to all of these. I'm not going to go through them in any detail because you'll very, very quickly get the taste for it, I'm sure. This is a truncated octahedron, and it's called that because they've chopped all the points off it again. But the same thing applies. If you look, this one's hexagons and squares, six-sided and four-sided. So if we imagined these four ribs growing apart and we joined them up, we'd have a square. So again, we can grow the truncated one. We don't have to chop bits off it, which I think is far more the way we're going. As we're moving into these shapes that are derived from these, we would expect them to grow, would we not? We wouldn't expect them to get smaller and have bits missing off them. It's rather a strange way of them putting it. Now, the same is true of all of these. They all do the same thing. They're all called truncated cube. You can grow one. You don't have to truncate it. The truncated cube, that divides a sphere into 8-sided and 3-sided shapes. The truncated icosahedron divides it into 5-sided and 6-sided. And the dodecahedron divides it into 10-sided and 3-sided. So effectively, with our 5 original shapes, we were using triangles, squares, and a pentagon. Now, for this second set of shapes we've got, for the feminine set of shapes, we're now having to deal with doubles of all of those. So we've now got 6-sided shapes, hexagons, 8-sided shapes, octagons, and 10-sided shapes, decagons. And in order to make these other forms, those are the only shapes we need. So I think we've got a picture of that springing from the Bessica. Hold on one moment. That's the way it goes. Right. So the next set of shapes we get are a further development along these lines, and only some of them actually grow. Oh, I remember the other two I wanted to deal with. That's why I'm having a problem. I want to return to this here, this shape. Now, does everybody remember this one? It's a mixture of a cube and an octahedron. It would look like, it looks like this. Now, when we last looked at that, we saw an upside-down triangle inside a bigger triangle, didn't we? I want you to imagine now that when you look at it, you imagine it with all of these points missing, with all of the points missing from the form. And when you look at that, what you'll see at the root of that is one of these. This is an extremely enticing combination of squares and triangles. It's coloured in green and yellow to show you that it's grown from the cube and the octahedron. And this one, Buckminster Fuller called it vector equilibrium. It's a very, very beautiful shape and one that we don't see around very much. And what it effectively is, it lives at the same level as those 5 truncated shapes I've just shown you. It's part of their family, and it lives between the square and the octahedron. The other one, this one here, which was also an upside-down triangle with a bigger triangle around it. Again, if we remove the points from it, we end up with a thing that looks like this. And this one is a mixture of pentagons and triangles. It's what sits at the roots of the marriage of water and ether. And that also lives in that first row. because there's 13 of those shapes, you can tell that there's only 6 more to go. And they actually, these have kind of been grown from the first set we started. The next lot also grow from the row that we've got to. It's quite a complicated process, but I'm going to start with this one. And what happens as they grow is that you have to imagine, the way it works is very, very hard to imagine this, but what happens is with that little cube octahedron there, we imagine that the faces move apart, so the squares and the triangles all move apart until they're as far apart as their edges are long, and when you join them together you get one of these. Now perhaps the best way of me showing that is to go away. Here we go. There's one of those 3D pictures. Are they all on here? In my world, I'm not sure. I think they're supposedly all there. Right, okay, well, so we can grow one of these from the cube octahedron. And what happens next is once you get to this one, we go back to imagining that the ribs move apart and we join them all together and we get one of those. Now, I've actually got a model of that so I can show it to you happening, but I will need about 16 hands. What's sitting in the heart of this shape here is one of these, okay? You'll be able to see this one's got squares all the way around its middle and all the way vertically and horizontally. And if you look at this, you can see it's got squares all the way around its middle, inside, and all the way around its vertical middle as well. And we can then see, if you look in the top of this and look at the square there, which is the square that's on the top of this one, okay? And what happens with that square is this rib moves to there, this rib moves to there, this rib moves to there, and this rib moves to there. And then they're joined together. Okay, so that gives you an octagon from the square. The 4-sided turns into the 8-sided. And so we end up, effectively, with one of these wrapped round one of those. And I did make some models specially for it and took some pictures of them, and they're not there. But I will be able to show you pictures of the other set, hopefully. So I love these shapes myself, these ones. And the other thing is here we get to see how the immune system works. Imagine you get something invading your system which is to do with this geometry here, and you want to plug it in. Then one of those will sit in there. You could also fit one of those cube octahedrons would sit in here if it was the right size. So we're starting to see when we get to this kind of level of growth that we get things that are going to fit inside other things. Now, those effectively grow out of that one there. Fortunately, the same thing applies to this one. If we imagine the faces of it growing apart, so the pentagons and the triangles all move apart until their sides are as far apart as they are long, when you join them together, you'll get one of these. And this one is actually dividing a shape into pentagons, squares and triangles. So now we're starting to get, that one there did it as well. This one's dividing into squares, hexagons and octagons. So we're now starting to see, as they get bigger, we're starting to see shapes made up of 3 different forms instead of 2. But it's still using the original faces that it used. You see, it's actually using simplicity to reflect upon itself and grow. These do the same trick, so that this one grows into that one when you move the ribs apart. And then if you imagine the faces of the ribs of this one moving apart, and again I'll show you it in a model in a moment, and you join them, you get this. Now look how this is almost spherical. This is the biggest and most complicated piece we get in this particular set. If you imagine that all of these were made, look how short the edges are on this one. If the edges were the same length as they are on the tetrahedron that we started with, this would be a really big form. And there we go. that is how this set works. You can see that we've got, we kick off with an icosahedron here and a dodecahedron. I've got these are the Lumino brothers, the artists formerly known as the Gray Twins, and they're there to give you some idea of size. Here's one of them. Hello. And both here. Hello. So those are that big. You can see them standing there, and you can see there, made out of magnetic sticks and balls, all the edges are the same length, so you can actually see the things getting bigger. This one's got 20 triangles in it. This one's got 12 pentagons in it. This one's got 20 triangles and 12 pentagons, okay? So we've got a melding of these two. This one's got the 12 triangles, the 12 pentagons and the 20 triangles, and it's got a number of squares on it as well, which I can't remember. But what it's done is it's expanded itself and filled its gaps with squares. The real big one, there we go. So that's how big they get. That's this one, the big one on the outside of here. That is how big they get when you make them out of sticks just about that big. So these shapes, as well as reflecting on each other and all growing from those original forms, they're also developing in size and complexity, but by using the simple means that they've already established. Can you see that? Nobody's coming up with anything new or flash here. They're just quite simply experiencing what's gone on before and playing with it, adding a little bit here and a little bit there, and getting extra size. So those two are here, in between those two. There's one missing. There he is. The smart ones amongst you will have noticed that there are two missing. If we're going for 13, we've only got 11 there. I bet you're counting. These other two are quite exceptional. They're the only two. You'll see that it's only the mixtures that have grown from that second level. But in that third level of growth are these two. The Earth grows a little bit more, and so does ether. And they do the same thing, curiously. What they do is they grow apart and then join themselves up with triangles. So this is 6 squares, and each square is surrounded by triangles, okay? And this is 12 pentagons, and each one of them is surrounded by a ring of triangles. So again, the same principle's been used to grow these two. It's a separate principle from those. But these also, for reasons that have actually got a bit of a left hand and a right hand to them. So you can build two different sorts of these. You can build one with a left hand twist and one with a right hand twist. All the others are uniform. And that, of course, is Earth and ether. So those are your basic shapes. Just going to have a drink of apple juice, which I didn't spill. And we'll move on to, those are the basic things. What I want to do is now have a little bit of fun with some of the shapes and see how they actually apply and how some hypergeometry and things like that. Is everybody happy out there? A quick question. Are you sure? There's some other expansion. That's the way crystal work, all the rhombic stuff. They'll all be versions of this kind of shape. But I've got a load of Archimedean jewels in the box behind me. If we're lucky, we'll actually get there, because those are shapes that you don't see very often. Let me just see how I'm going to handle this. I'll just have a quick refer to all my pictures again. And, oh, okay, let's have a quick look at growth, shall we? So we see now these things can just grow by reflecting on each other, and so long as they keep the same length side, they just get bigger and bigger by growing from each other. This is a picture of a Fibonacci spiral. And we can see that this spiral here, which I have drawn, is pretty much the same as this one. Now, we've talked about the Fibonacci numbers a lot here. They go 0, 1, 1, 2, 3, 5, 8. And the way they do that is 0 and 1 added together is 1. So the third number is 1. 1 and 1 added together is 2. 1 and 2 added together is 3. 2 and 3 added together is 5. 5 and 3 added together is 8. 8 and 5 added together is 13. 13 and 8 added together is 21, and it goes on to infinity. And what this is a picture of that process. Here's a little box which is 1 by 1, okay? And then the next box we get is 2 by 1. The next box we get is 3 by 2. The next box we get is 5 by 3, that one there. The next box is 8 by 5. And then you simply draw a kind of radial curve right the way through them. And this is everywhere in nature. We can see it here in the fern, but can you see it's also in the little bits of fern that are going to curl off the big bit? It works. Another place it works where I think it's really fantastic is John earlier was talking about a meandering river and how it's really important to keep water flowing properly to keep the meander in. Well, actually, the meander of the river against its straight line is also in phi proportion. So this kind of growth pattern also applies to the way a river runs. Its curves against its straight. If you say the straight is 1, then the curves will be 1.618 long. So that is the standard way of growth. We've seen it in snail shells, you see it in ammonites, you see it everywhere. It's called phi. It's the divine proportion, and it does all sorts of very clever mathematical tricks as well, which we won't have time to get into. I've only just started gripping those myself. A way a triangle can grow like that. You can actually see how there's one in the middle and then another one and then another one. It just grows bigger and bigger. But here's a more interesting way for triangles to grow. I love these. This is called a Sierpinski sponge. Start with a tiny tet, okay? Now, each one of these is made up of 4 of those. There's 3 on the bottom with 1 of them on the top, okay? And the same with this, and this one's made up of 4 of those, okay? This one here is made up of 4 of these. And you can see there's a gap, triangular shaped gap there, then a bigger triangular shaped gap there, and then a bigger triangular shaped gap there. And you can just keep building them. I've seen ones on the internet built out of these magnetic sticks and balls, and they're massive. And they will support each other. The triangle, the tetrahedron is so strong that you can just do that and you can just keep building it. I would imagine it's a right pain in the arse when it all collapses and you've got to take it all apart and put it back in the box. But that is a fantastic way of triangles growing, and the reason why I think it's called a Sierpinski sponge is these different size holes and stuff in it must make it extremely good at soaking up fluids. Okay. Oh, I'll just give you a picture of that. I want to show you that as well. There's your fractal that I couldn't show you earlier. And there's a fractal cauliflower. So it's like a man on a vegetable. So that's a little bit of stuff about growth. Some of these things form together. This was another thing. We called them platonic solids, platonic forms. That particular shot that's turned up at one stage, I think these were found at Skara Brae, this particular set. But the point is they're very, very old indeed. Because they're stone, we're not quite sure how old they are, but I've also seen a set that's made out of crystal. And they all come from well before Plato's time, we can be sure of that. But here you've got effectively got a dodecahedron, an icosahedron, an octahedron, a cube, and this is probably a tetrahedron. They did cube octahedrons as well. So they had a good grasp of these basic geometries. They would have seen them in the world around them, I'm sure. And when we talk about hypergeometry, which is where I want to go to next, when we use the word hyper, we just mean the level above, okay? So a hypersquare would be a cube. And a square is a 2-dimensional item, a cube is a 3-dimensional item, so a square is a hypercube. A cube is a hypersquare. One of the easiest ways of thinking about hypergeometry as well is with the cube. So if you imagine we've got one cube here, okay? If we imagine that we stick a cube, imagine we got another 6 cubes, Ross, and we want to stick one of those 6 cubes onto each of the faces of this. So what we end up with is a 3-dimensional Swiss cross. Can everybody imagine that? And then if we imagine that we've got another great big cube that we wrap around our other 7 cubes. Now here in the 3rd dimension, the 7 smaller cubes won't fit inside each other because they're same size, nor will the big surrounding mother cube fit inside them all. But in hyperdimensions, out in the 5th dimension and beyond, all of those cubes could fit inside each other. So all the small ones could be fitted inside each other, and the big ones could be fitted inside all the small ones. Now, obviously, in order to pull that kind of geometry through to the third dimension, we have to lose a little bit of stuff. And here's a nice example. Here's another hypercube. This is a hypercube made out of brass. It's called a tesseract. It's a very magic little shape. I advise you to come up and have a play with it afterwards. The thing is, can you see how there's kind of squashed cubes in here? There's the face of a cube, there's another face of it, and it's wedged in there. There's 4 of them on that side. Can everybody, you might have trouble seeing them because it's a bit of a way away from you. But the idea is it's got 1, 2, 3, 4 cubes on that side and another 4 on this side, and they're all springing from a point in the middle here which we can't see. They're kind of exploding into our reality from there. So in order to see this hyperform, we've lost the actual shape of the cube. This is a lovely little thing, this is. This really turns the head of guests when they come around and they find one of these sitting on the table. It's a dodecahedron, so it's one of these. But it's had a 5-pointed star inscribed into each of its faces. The reason why this was made was because some bright spark asked us why it was that Plato associated this with Earth when John Dee, Queen Elizabeth's chief sorcerer and fortune teller, connected this with Earth. So this was made to try and sort out that riddle, if you like. And what we found with this is that if you take one of the lines of a pentagon like that, a pentagram, let's call it, rather than a pentagon, and you put your index fingers on it, and then you take a line from the next pentagon and you put your thumb and your thumb on it, you can see that I've got a square, yes, in there. If I now take these fingers, whatever they're called, my ring finger, and put them underneath my index finger, I've got another square. Okay, so I've got a square on top and a square on the side. Yes, everybody happy with that? And then if I put my little fingers on these here, I've got another square on the back and another one on the bottom. So I'm actually holding a cube inside this dodecahedron, yes? Now the thing is, if I move my fingers round to the next line on the pentagon, I've got another cube. So effectively what there is in here is like 5 virtual cubes vectored into each other. We did spend some time with a needle and thread trying to just get one face of each of the cubes in place, but oh god no, we had to give that up. It will happen one of these days, but again I invite people to come and play with this afterwards because that's quite spooky. What's happening there in order to bring the hypergeometry through is we can't actually see it. We're losing all sight of it altogether. The perfect piece of hypergeometry is of course this star-tet down the end, because if you remember we started off with a tetrahedron with a baby upside down tet inside it. So to start with, the little shape is the same as the big shape, which wasn't the same with any of the others. The other thing is that as that little tetrahedron inside grows, as its corners pierce the triangles in its parent tetrahedron, they're little tetrahedra. Right from the word go, they're always tetrahedra. And what we see with the actual shape itself is that, although it's one upward pointing tet and one downward pointing tet, all of the things on it are tets as well. And I had a lot of fun with these when I started because I thought, I know what I'll do. I'll make a big tetrahedron and then I'll see what it's like if I make some half-size tetrahedron and put them on it. I was thinking I'd get something a bit like the cauliflower, you know, a fractal growth. But actually, if you get a tetrahedron and stick 4 half-size tetrahedrons on it, you get one of these. I thought, oh look, it's another star tet. And the next thing I did was to take an octahedron and make a load of tets and stick them on it, and you get a star tet out of that as well. But obviously if you stick 4 tetrahedrons on here, 8 tetrahedrons on here, you are going to end up with something that looks like that, you know? And if you look carefully inside this star tet at the end here, you'll see that there is an octahedron in it. You see it in the middle here? There's actually an octahedron in there. And if we remember, that's the symbol for fire. The tetrahedron's the symbol for fire. So fire and fire gets air in the middle of it. I really love that. I like the mixture of earth and air as well, because that's called Adam's Earth. It's obviously the mixture of earth and air which enables us and all the other living beasties to be here. Here's a piece we haven't seen. Here we go. Now here we're going to start looking at the shape of the sub-ether here, because this is, I'm going to need that. Because what this actually is two star tetrahedrons. If I hold it like that, can you see the two star tetrahedrons right next to each other? Well, I can prove it to you by adding this star tet to the end, okay. Right, so everybody's happy with that. We can see we've got two star tetrahedrons here, and there's another one. Now, if we look carefully at this piece here, you'll see facing you a square, okay? Can everybody see that square in the middle? Just here. And if we look round that square, we can see that it's got a triangle here, and a triangle here, and a triangle here, and a triangle there. And we've seen that shape before today, have we not? This one, the cube octahedron. So, sitting in the middle of your two star tetrahedron is a cube octahedron. This turns out to be the absolutely central piece. When I stuck that other star tet on the end of it, there was another cube octahedron in there. Now, I've actually got a shape which is unfortunately away being repaired at the moment, but it's made up of about 9 of these set next to each other and on top of each other. And what it actually makes is a giant star tetrahedron bounded by a giant cube octahedron. You won't be able to see that this time round, but it's a fantastic shape. And the other thing is that our cube octahedron in the middle of this has got a load of lines going into it, okay? It's like just like that. Here we go. So here you've got a square with the triangles around it, and with all of the lines pointing into the middle. Okay. A really fantastic shape, and that's what's exactly in the middle of those two there. Now, sorry about your tackle, guys. You have to take it out with wages. Up here we've got a cube octahedron with the stellations pointing outwards. Now, I like to imagine that inside there is a cube octahedron with all the things pointing inwards like this, energetically, and then right in the middle of that is another cube octahedron with them all pointing outwards, everything nested in and out forever. And the punchline, if you will, we've probably whipped through this a bit quicker than normal because of the slightly scrambled approach, so I'm sorry for that, but the kind of punchline of this piece is here. Where's my string? There it is. Okay. So that's flower life. Okay. But it's a 3-dimensional flower life. And the first thing we notice about it is that can you see it's got a square shape pointing towards you with the 4 triangles off it. So it's actually a cube octahedron in a square form. The plates themselves are round, so we've got 6, if you like. Where's it gone? Is it reachable? We've got 6 of these kind of interlaced. So they're all round like this one is, and yet when we spin it, you'll see that it goes round and then egg-shaped. We call it a Genesis egg. Beautiful thing. But not only is it a cube octahedron on the outside, it's also a cube octahedron on the next level in, and a cube octahedron right to the middle. So it's actually cube octahedra nested inside each other, and then it's formed round these things here. It's formed round the spikes. Now, so effectively the one I've got which is 9 of those arrays all stuck together, is the shape of the kind of ether. It is the kind of basic pattern upon which everything is built. But because everything's spherical, it actually ends up looking like this rather than looking like a cube. So that's where it all goes to, guys. Your cube octahedron is the most central thing, and that is how your apparently circular flower of life fits into the cube octahedron. Now we have one more bit of fun to do as we slip back into the nominal world of plane geometry. Stay. I need to find nice scissors. It's been that bad, I'll just... Right. Okay. So, we're working our way back down now towards the end, and I can feel beer o'clock coming upon me. Obviously, we've prepared these beforehand, but I'd like you to imagine that they were just a strip of pink paper with white on the other side. This is a perfectly normal strip. It will do exactly what we expect it to do if I cut it in half, which I will now do adeptly. Here we go. Oh, it's going on forever, look. Now, no surprise there. How many people have heard of amoeba strip? Excellent. Now these, man, you get loads and loads of fun out of some cheap paper. Do it on a pair of scissors with these. This one has been stuck together with just half a turn in it. We've just turned it half a turn and stuck it together so that now if I run my finger around it, okay, it goes pink and on the pink and on the pink and on the pink, and it's still on the pink, and it's still on the pink, it's still on the pink, and then it's on the white. And if I now run it round the white, like that, it's still on the white, still on the white, still on the white, still on the white, and now it's gone onto the pink. So we have made a very strange three-dimensional thing out of our apparently two-dimensional, obviously not really two-dimensional. And this one is going to do something quite surprising when we chop it in half, because if I work my way all the way around it, this is one you can't prepare earlier because people wouldn't believe you see. I cut it in half like that. And what it makes is an infinity sign, okay? Now, I used to say if I had an infinitely sharp pair of scissors, I could go on doing this and it would just get bigger and bigger until some smart arse turned up and picked up the scissors at the end of the talk and said, no, look, this is what it does. So now I've got to go all the way around it again for your benefit. It's a funny story attached to this because we also heard a tale about a young lad who was going round the playground betting all his mates that 50p that he could climb through, could cut a postcard in such a way that he could climb through it. And once I thought that this must be the technique that he was using, but when you get actually to the end of it, which I will do in a minute. Talk amongst yourselves. Oh. I normally have a bigger pair of scissors. Come on, you rat. Have I missed me? This time it's gone into 2 infinity strips. Now, more strange stuff happens if I cut those in half, but you'll be glad that I'm not going to do that. But would anybody have expected it to do that? I really don't think it's quite right that two-dimensional stuff should behave that way, but it gets even more strange. This is the same as the other amoeba strip. It's got half a turn in it, but this time I'm going to start cutting it on my left or your right, whichever you prefer. By the way, the lad with the postcard, it is possible. Rianne, my friend, we actually got a postcard at home which she worked out how to cut so that you can actually step through it. So at some point we might go down the pub and try and earn some 50p's from people. But lost my way. Have to go. What's happening here? Ah, well, that's a mystery. What's going to happen here isn't what's supposed to happen at all. I'll try again on this one. That's going to be easy, because normally what should happen, hopefully it will, but as I cut my way round on the left-hand side, I'm supposed to find my way. Do me a favour, mate. Off you go. Thank you. It should do. It should do. They say simple tasks get more complicated in front of experts. There we go, it's worked this time. That's where I started my cut on your right and my left, and I've now turned up here on my right and your left. And if you keep going around, that's not going to work either, is it? No. Sorry, screwed that up. Never mind. There you go. There was something wrong with the Amoeba strip. What should have happened there, and that should have been the finale, so that's a great way of finishing, isn't it? What should have happened there is you actually end up with one little ring and one ring that's twice the size by starting a third of the way across. Or probably it's a third and 2/3 or something. But that is how odd things get when you just get flat things, put half a twist in them, stick them together and start dividing them. And of course our DNA's got twists in it, hasn't it? So we've been looking at the way spheres divide into equal portions, and there right at the end we've been looking at what a difference a little twist can make to this or this straight geometry. So all of this stuff just goes straight using straight edges and angles. As soon as you start putting a twist in things, you start, just imagine the potential for this simple stuff once it's starting to twist. But that's it really. You've been introduced tonight to the dimensions, to the 5 platonic shapes, to the 13 Archimedean shapes, and to several other things. And actually, I'll remember, there's 1 or 2 other things I want to show you. Are they about? Yeah, here they are. Right, do these first then. I've got some little crystals in here. This one's a piece of iron pyrites, and this is how it came out of the stone. I saw this actually come out of a bigger version of itself. It came out of a block. This is slightly, not quite square, it's rectangular, but as we were looking at it, this just slipped out. I've got in here, and I'll fish it out in a minute, I've got another piece of iron pyrites, which is broadly dodecahedral. It's the same shape as this. I'll fish it out in a minute. In fact, I'll fish it out now. I'll have to find it afterwards. Things continue to go swimmingly. So, we'll have a look at these instead. This is a tiny little piece of garnet, rough garnet, which is exactly the shape of an octahedron. And this is a little bit of hematite, which is also exactly the shape of an octahedron. Shape. This is another piece. This is a rough garnet. I invite you to come and have a look at this afterwards, because it introduces us to another set of 13 shapes. So I'm not going to show you all of those, but you remember how we got an octahedron by putting dots on a cube and joining them up inside? Well, the good news is that those second set of 13 shapes that we've been looking at, if you put a dot in the center of the faces of all of those and join them up inside, you get a whole new 13 set of shapes. And they are really interesting because, here we go. Here's the one I'm particularly interested in. This is a shape you get if you put the dots into the centers of the faces of a cube octahedron. And it looks really unnatural. When I hand this out to people, they go, no, that's not right. It kind of looks like 4 cubes in the space of 3. It was my shape of the year for at least 2 years running. But imagine my surprise when I was given this piece of rough garnet, which I swear you can come and have a look at it yourself, folks. This is the same shape as that. So the crystal world knows about Archimedean jewels. And whilst we're on the subject of the Archimedean jewels, there's a couple of other interesting points about them. This is the Archimedean jewel for the truncated octahedron, look, and it looks like a cube. Can you remember how the green and the yellow went together? How these two were reflections of each other? Well, as this octahedron grows, it becomes something that's really like a cube, okay? And as the cube grows, it becomes something that's really like an octahedron. So what we're seeing there is something that the old alchemists understood really well. They understood that the fixed and the volatile were not different things, that over huge periods of time, the fixed would become volatile and the volatile would become fixed. And that is exactly the process we see happening here in geometry. The other shapes on these are really beautiful. I haven't made the full set, but this is your this is the one that grows from the dodecahedron, and it looks like an icosahedron, yeah. And the same is true of the icosahedron as well. It tends to look like a dodecahedron by the time it gets to this point. So they've kind of grown through a whole journey. It all developed from these really, really simple things that we started with, those three shapes. The other thing I'd like to point out before I leave you is that feminine geometry has been very invisible to us. You all have seen the Platonic geometry, but you won't have seen so much of the feminine. It's coming much more to the fore now. The only two bits of feminine geometry we do see a lot of are the one that we called the truncated icosahedron, made of pentagons and hexagons, looks like this. Probably don't recognise it looking like this, do you? No, I've never seen that before. How about this? You know what that is? Same thing, just coloured differently. So this piece of feminine geometry, one of the few that's made it through to the 20th and 21st century, we kick around on a muddy field on a Saturday afternoon. It was pointed out to me when I brought that up that the other piece of sacred feminine geometry that we see is the Vesica Piscis. Vesica Piscis here, but in 3D. If you turn it around, it's a rugby ball. So we get to see that kicked around on a Sunday afternoon. So that's me, folks. Thank you very much. You've been very patient. Sorry it's not been quite what I intended. Thank you. Oh, you're so kind. I have got some DVDs at the back here. One of them is of me doing an alchemy talk, which is another thing I talk about, and one of them is an interview with me. It's the first ever DVD interview with me, so I'll never be that honest again. It's basically a guide to the many madnesses of Nick M. They're in my boxes back here, but they're $5 each. I've also got a set of painted slates here. I paint geometry onto roof slates. Some of them glow in the dark, so we might be able to see this. The first time they've ever been out in UV light, really. So I'm going to try and clear this geometry away. Hopefully round I'll come and put some more of my stuff on there, and we'll call it quits. I'll try and get out of the way for the next person. But thank you very much again for being so attentive. I think you've worked really hard. Ta.